Our presenters today are Mark Lewis and Dr. Tracy Gibson. I'd now like to give you some background on our two presenters. Mark Lewis is a system engineer at NASA Kennedy Space Center. He holds a BS in electrical engineering from Cleveland State University. Mr. Lewis has over 30 years of experience at NASA, working on numerous research and spaceflight projects at Glenn Research Center and at Kennedy Space Center. Mark has research experience in the development of damage detection and health management systems and various types of gas sensors for use in launch systems operations, spaceflight experiments, and biomedical applications. His flight hardware development experience includes satellite servicing and microgravity physical science experiments. Mr. Lewis holds 7 patents and is also listed as an innovator on 22 NASA technology reports. Dr. Tracy Gibson is a subject matter expert scientist for the Laboratory Support Services and Operations contract at Kennedy Space Center. He holds a PhD in chemistry from Florida Institute of Technology and a BS in chemistry from the University of Southern Indiana. Dr. Gibson has supported numerous research projects, including projects related to materials development and in situ resource utilization. He has research experience in developing methods for the capture and processing of the Martian atmosphere and converting waste products into fuels. He also has research experience in the development of self-healing materials for aerospace applications, novel magnetic materials, damage detection systems, as well as development of systems for intelligent thermal management. Dr. Gibson holds 14 U.S. patents and 1 U.S. patent pending. He also is listed as an innovator on more than 90 NASA New Technology reports. Following today's technical presentation, I'll be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to Mark and Tracy.
Hello, good afternoon. My name is Mark Lewis. Thank you, Lou, for that nice introduction. I work at KSC. I'm in the Exploration, Research, and Technology Programs Directorate. And as Lou had mentioned, Dr. Gibson will also be co-presenting these slides. So we're going to kind of take turns doing it. And before we go ahead and get started, I'm going to go ahead and turn off my video just to make sure that we save on bandwidth. So let's go ahead to our next slide, please. So today's agenda, we're going to provide a background of damage detection technologies that we've been developing here at Kennedy and also their evolution. And we'll be able to go through basically the progression of all the different capabilities, testing and demonstration, and then also we'll be able to answer some questions. Next slide, please. So just a little bit of background. MMOD are serious threats to the ISS and to extraterrestrial habitats. And NASA classifies MMOD as a primary threat to commercial crew vehicles. And in 2014, the ISS team assessed a P4 photovoltaic radiator damage that was caused by MMOD impact, and it resulted in a 12-inch long puncture to the cover sheet. And so structural health monitoring and damage detection technologies are identified as critical needs in multiple NASA technology roadmaps. Next slide, please. So we have extensive experience developing damage detection technologies for over a decade. We have 3 patents listed here for technologies that we're going to be presenting today. But there's also other related technologies with regards wire damage. We also demonstrated a single panel system for HDU at Desert Rats. You'll see there in the upper right-hand corner, our system is side mounted on the HDU. And that was done out in 2011 out at Flagstaff, Arizona for that. And then the next year in 2012, we demonstrated a multi-panel system where we integrated data with crew display avionics for HDU And we did some remote testing capability using secure network between KSE and JSE. And so you see those pictures on the bottom going from left to right. You'll see a screenshot of the integrated crew display, and then a picture of our LabVIEW system display, which was custom developed in-house. And then also we have a photo of the system along with the 3 panels mounted on the HDU. Next slide, please. So MDDS, it's an intelligent damage detection skin. It can be attached to structures or it can be embedded into composites. The technology is based on sensing electrical integrity of conductive traces. So when an impact occurs, or in some cases, even when cracks or delaminations, mainly cracking in composites, when those things occur, those traces are broken. And so there are several sensing layers that can be implemented in a desired pattern. And as we'll discuss later in the presentation, those layers could be alternated and be arranged orthogonally, creating a grid pattern, or they can also be arranged linearly as finger-based panels. Also, the design is tailorable. It can be used for interior and or exterior applications. The sensing material, size, and trace spacing can all be customized depending on the application of what you're trying to detect damage for. It provides a lightweight in situ health monitoring capability for spacecraft, for expandable structures, and also for terrestrial applications, such as for wind turbine blades. MDDS consists of 3 main subsystems. We have the panels. We have an interface board that has embedded software for situational awareness and damage detection. And then we also have a mobile device that has a GUI that we can operate and monitor the system. Next slide. So the architecture is flexible and expandable. It can support 1 or many sensory panels, and it can be organized 2-dimensionally in linear or grid patterns. Some attributes regarding the panels is that depending upon the application, they can either be active or passive. They have a very low power consumption. Typically, we run voltages of around 3.3 to 5 volts DC, and so they can be powered by battery or powered via power supply. They're also interchangeable and modular, so the exact same hardware and software reside on all panels. They also can operate independently or as a multi-panel system where a master panel can control, monitor, and coordinate information from the other panels. The GUI allows users to configure, command, and monitor the sensory panels wirelessly. And so we'll go ahead and turn it over now to Dr. Gibson, and he's going to tell us a little more about those sensory panels.
Next slide, please. And thank you, Mark. So I'm going to on the next few slides talk about the evolution of our sensory panels. And so the Generation 1 panel really started back in the early 2009, 2010 timeframe, when we were looking at printing conductive carbon nanotube-based inks onto flexible substrates. And so we developed technology at Kennedy Space Center to be able to inkjet print conductive inks onto polymer substrates. And using this technology, we decided to print our first generation of sensory panels. And so on the image on the right, you see the Gen 1 is 4 panels. That's actually a silver-based conductive ink that is printed onto a polyimide substrate using a HP inkjet printer, a color inkjet printer. There's also a little photo to the right that shows what the silver ink traces look like. They're about 20 mils and 20 thousandths of an inch in width. And in order to assemble these, we had to have a special jig, and that's what you see in one of the images below, the Gen 1 panel fabrication jig. And then to the right is the 4-layered panel that's assembled. Due to the complexity of printing these panels and the fact that it's very hard for an inkjet printer to print a continuous straight line across a long distance, we went with a outside vendor to start fabricating and producing these boards, and we were able to actually have an outside vendor produce us these flexible printed sensory panels, and that's what you see in the Gen 2 panels. The reason that it made it complicated is the first generation and the second generation, the sensory system was put together using a compression system that allowed the panels to be removed freely, and it required all of the individual traces to line up perfectly with contact pads on the rigid circuit board, and that was complicated when we were printing with the inkjet printer. We had some issues with some slight movement of the prints, so we actually went out and had these fabricated, and they turned out very nice. And you can see in the image on Gen 2, the one on the left is the front face, and they have Kevlar panels in between the 4 layers, Kevlar sheets, and the image on the right is the back side. Next slide, please. The Generation 3, we decided we focused a lot more on the embedded software and instead of on the sensing layers. And so we actually designed a system that has a 2-layered sensory panel that has everything on board, including the microcontrollers, the embedded software, and the Bluetooth wireless communication. An image is shown here of the 2 sensing layers. They're orthogonal to give us a 2-dimensional grid. Each sensing layer has 96 parallel conductive traces, and the spacing between is roughly 50 thousandths of an inch. Again, one of our goals was to have this very low power, so the power consumption was less than 500 milliwatts per panel. And the overall dimension was about 9.5 inches by 9.5 inches by 1/16 of an inch thick. And then there's a notional architecture image to the right that kind of shows how this would be laid out in a 4-panel configuration. And it shows the different Bluetooth connections and the communications within each of the panels. Next slide, please. And so now we're getting to some of the more recent work, which was our Gen 4 system, and this is the most current system. And we decided to focus on the ability to embed our sensory system into composites. And so to do so, we decided we were going to use flexible thin printed circuit boards and embed these into the composite structures and use these flexible circuit boards as a monitoring system, much like what you had seen in the other systems. And so the image on the left shows panels, or what we call them the 2-finger and the 4 or 8-fingered sensory panels from 2 different vendors. The main difference between these two is the thickness. The image, the ones that are a little bit lighter color are about a 32nd of an inch. They're really thin, 32nd of an inch thick or thinner. And the ones that are a little bit darker are slightly thicker. These are polyimide substrates that they're printed on. On the right, you'll see the laminate test specimen. And so this is using a G10 plate to simulate a fiberglass sheet, and we have a front and a back face. And these are essentially, when they're laminate, essentially there's only one face sheet used. And so we're simulating if you were to take an existing structure, and these would be adhered to an existing structure. Below that is actually one that's fully encapsulated, so it's composite. So there is a front and a back face sheet, and the sensor panels, or the 2-finger sensory and the 4 or 8-fingered sensory printed traces are actually embedded inside the composite. And then the last thing shown here is a painted on version. And so we decided to also look at something, not just a laminate version where you could actually adhere a prefabricated thin flexible circuit board to the circuit, or conductive traces to the board. We could actually print this onto the surface. And so we actually made a version, and there's stencils that were used to print a silver, or to apply a silver paint, conductive silver paint to a surface. And then leads were attached, and this was primarily used to monitor for cracking in an existing structure. Next slide. And I think, Mark, this is where you could take back over.
Yeah, thanks, Tracy. So just as Tracy was talking about the sensory panel evolution, we also how we interface to these sensory panels also evolved. So you'll see there on the right, in that top right image, that's our Gen 1 and Gen 2 multi-layer panel. It's got numerous conductive traces. In fact, it's got it's a total of 4 layers with 168 traces on each layer for a total of 672 traces. And so as you look down, if you move down into the Gen 2 sensory panels with the compression ring, so as Tracy had alluded to before, we developed this solderless method to basically interface all these 672 conductive pads to the interface panel. And we did that using a compression ring. Now, this particular ring on the interior diameter is about 6 by 6 inches. And we also used a rubber gasket between the interface, and we basically compressed the interface to hold it. Now, during the assembly of those panels, we also needed to use a jig to make sure that we had good alignment, so that way those pads would align to the mating pads on the circuit board. Now, we changed our design a little bit, again, looking at a little bit different direction, and that's where it leads us really to our 4th generation. And this is where we started going with this finger-based sensory panels that Tracy alluded to on the previous slide. And so you see there's 4 ZIF connectors, and we can, these boards can be powered up, basically either being battery operated, or they can run off a 5-volt power supply through the USB port. They also have a Bluetooth transceiver on it, so it can handle Bluetooth and communicate with the data from the Bluetooth. And so those 4 fingers, if you were to put the full complement of those 4 fingers with a total of 12 traces on each finger, then one board could have the capability of monitoring 48 embedded traces. And so the board is about 2 inches by 4 inches. And so it gives us a nice way to interface, especially with those ZIF connectors. Next slide, please. So now let's talk a little bit about the software. So again, over the years, our software evolved. And so during our Gen 1 and Gen 2, the embedded software was only monitored and reported electrical integrity of the conductive traces. So we were using a 16-bit PIC microcontroller at the time. And so we basically were running C in an assembly language to monitor those conductive traces, and we would interface to those panels with a GUI, a custom developed LabVIEW software. It provided our GUI. It also gave us a capability to be able to process and identify the results in terms of where the damage occurred. It also gave us the capability to visualize the impact data, and also gave us the ability, it's hard to see in this image, but there's different color-coded layers. So depending upon, again, the first generation, we had 4 sensory layers. We could detect if damage occurred on the top layer, the second layer, or if damage occurred on all 4 layers, and it would be color-coded as such. Well, then for MDDS, again, our software evolved, and this time we wanted to embed, in particularly, we wanted to get the damage detection algorithms, we wanted to get the wireless communication, we wanted to get the situational awareness, all these kind of algorithms and capabilities embedded into the actual microcontrollers, into the boards themselves. And so we did that. And so basically, the embedded code, it executes some algorithms there. It determines the master panels, which we'll talk a little more about in this configuration about master panels. It assigns the master panel via GUI. It also generates an active panel map, which we'll talk a little more in the next slide. And also it monitors the health status of all of the active panels. And it acts that master panel kind of acts as a global coordinator of all of the other active panels. So we'll talk a little more about that on the next slide. So the initialization, just a little bit about the initialization of this embedded code along with the active panel map. So each panel, when it starts up, it checks for the presence of an active panel to its left and or below it. And it does this using an I² serial interface. And when it goes through to do that, it's looking to determine whether or not I'm a potential master panel. And if there are no active panels that are present to the left or below it, it assigns itself as a potential master panel. And then it configures the Bluetooth transceiver. Now, one or more potential master panels could be present depending on the configuration, because the configuration is arbitrary. It could be a very interesting configuration in terms of how you have it tiled, the different sensory panels. So once the user assigns a master panel using the GUI, all the other panels become normal active panels. And so this newly assigned master panel then starts progressively scanning using this active panel mapping algorithm to determine the spatial relationship with all of the other panels in the system. And so it communicates with the adjacent panels to determine its closest neighboring panels. And then it requests adjacent neighbors to report status of their respective neighbors until there are no new panels to be found. And then it maintains a record of that configuration and also the path, so that way it can access those active panels later on. Next slide. So each panel, as I mentioned, continuously monitors its own health. And the damage detection algorithm evaluates the health status by injecting some test pulses periodically on the sensing traces to determine the electrical integrity. And again, as before, if the traces are broken, then the algorithm calculates the location of any faults. And then the relative timestamp is also associated with each damage event, so that way you can establish an order of events. And it also helps to organize and identify the location of damage if subsequent damage occurs later on to the panel. The GUI then periodically requests health status from the master panel of all of the active panels. So the master panel then takes and gathers and coordinates and packages all the data from the other panels and then sends it wirelessly to the GUI. And then the damage location is reported in a rectangular boundaries. And you'll see a little more of this on the next slide, but basically the bottom left-hand corner to the upper right-hand corners. And then when damage is detected on the top sensing layer only, then because we can't resolve a Y coordinate, it's undetermined where the exact location of the damage occurred. And so it only reports the x-axis only. And let's go into the next slide, then we'll get a little more detail on this. So the MDDS GUI, it was written in Swift, and it was designed for a 3rd generation iPad Pro. It could run on many other different iPads if needed. The software would be updated. The GUI allows users to configure and command and control and monitor the status of the sensory panels. And it receives the telemetry wirelessly from the master panel using Bluetooth. So an operator would basically press up at the top right-hand corner of that screenshot of the home page. It basically press scan. It locates the master panels that are potential master panels, and then it assigns the panel. The operator would assign a panel, and then you can open up a session to begin communicating with that master panel. Next slide, please. So we evaluated the app's performance using some simulated test data. And so the data set consisted of 5 sensory panels that were laid out in inverted T's. So you see the image there, to the left. Those were the panels and how they were laid out, and they were connected using the I2C interface, as I had previously mentioned. Now, during the operations, as we kind of talked before, during that initialization, the panels are going out trying to determine who is a potential master panel. And so once they go through that initial operation, the user then scans for the Bluetooth advertisements and finds whichever ones that are potential master panels and configures and assigns that particular master panel. And then it opens up the communication thread and service, and then it goes ahead and starts sending and receiving information wirelessly. And so then the sensory panel also is able to show health information displayed. And so if you look at that home screen now, you'll see the layout. So you see the graphical layout matches the physical layout of the test panels. And so in this particular example, and we're going to go into a little more deeper dive of this in the next slide, but you'll see that the red filled graphics indicate a panel that has damage. The green filled graphics indicate panels that don't have damage. So let's go to one of those panels that are indicating a red or damage by going to the next slide, please. So when you click on that panel, and particularly panel 2,3, you'll see that on the right-hand side, this is what the GUI shows you for that panel. So it gives you more of a detailed information regarding that panel. So you see there 3 rectangular squares in red. And so that red and those rectangles are indicating that we had broken conductive traces that occurred on both the top and bottom sensing layers. So that way you could actually resolve an X and a Y coordinate and be able to pinpoint where that damage was located. Now in the yellow, you see there, that yellow rectangle, that was damage that occurred only on the top layer. And because there were no Y coordinates that could be assigned because the conductive traces were not broken, then all you can say is that somewhere along that line, along that particular rectangular area, that damage occurred, but you can't say exactly where in the Y coordinate occurred. And then also we give some tabular information. So we assign a damage ID number. We also provide the coordinates in terms of the left-hand corner and top right-hand corner, X and Y coordinates. And then also we calculate the width, the height, and the calculated area are all displayed there on the iPad. And I think that covers us for the GUI. I think we'll now go over to Dr. Gibson, and he'll be presenting the remaining slides.
All right, next slide, and thanks again, Mark. So the next few slides, we're going to really talk about the testing that we've done more recently when we were actually taking the thin flexible circuitry and embedding it into some composites and also doing the laminates. So the samples that we produced, the test specimens, were subjected to 2 types of testing. They were a 3-point bend and then a low cycle of threshold fatigue testing. And so in the 3-point band testing, it was per a modified version of ASTM D7264. And the modifications were really necessary due to the differences in between the test specimen and those that are required by the standard. And our overall goal of this testing was to determine if the failure of the fiberglass face sheets could cause ripping or tearing or damage to the adhered flexible circuitry inside the composite or laminate. And then the low cycle threshold fatigue testing used a similar setup to that as the ASTM D7264. And the testing was conducted where the specimen was subjected to low load and high load for 100 cycles. And then after 100 cycles, we attached it to our interface board, assessed the damage. If no damage was observed, we repeated increasing the loads until we actually got failure. And so here's a video showing kind of how we did that low threshold flexural testing. And I apologize that it's a little choppy. This is actually very uniform and smooth testing. And so, again, I kind of apologize that that looked a little choppy, but I think you get the idea of how the testing was done. Next slide, please. And so I'm going to discuss a little bit about the results here. And so the first is from the 3-point bend. And I describe these two ways. I describe a composite, and again, going back to my definition of what this is it's that the flexible printed circuitry is inside between two layers, two face sheets of material. In this case, they're fiberglass. And then if I describe a laminate, it's where only one face is attached to in this case, the G10. In the composites, the fully encapsulated, the 2-fingered thin flexible circuitry that we attached showed damage in all cases after the composite failed, and that's what you see in the image on the right. You see where the break occurred, and like they said, that was from both vendors. However, the product from vendor A, which was the little bit thicker product, didn't really show damage until the sample was kind of flexed. So it showed that the embedded circuitry was damaged, but it wasn't like a complete clean tear. It had damaged it enough that once it was flexed, it fully separated, but it did not do that until it was flexed. The other thing that impacts this is the thickness of the face sheets. These face sheets are pretty thin. And we know for sure that the thicker the face sheets, we're more likely to see that the bigger impact on our embedded flexible circuitry. And then on the laminated system, which is the one you see a little bit lower, you can see where the damage occurred. We are absolutely able to see the damage and the tearing, and we actually looked at these under a microscope, and you could see the physical tearing of the embedded circuitry there. The fatigue testing, unfortunately, didn't provide quite as conclusive results where we were just flexing it. The problem really ran into is that we were flexing and not seeing much damage, and we continued to increase the load. And then, lo and behold, the systems actually failed, and we didn't really get a lot of good data. We are trying to develop a process to do this data acquisition real time to see if we could see the damage while the flexing was occurring, but we did not have time to complete that due to some funding constraints. Next slide. So that pretty much sums up or finishes what we've been discussing. So just kind of sum it up here, saying, KSC has been developing and demonstrating damage detection technologies for more than a decade. In particular, the MDDS provides an attractive option for applications where in situ health monitoring is desired. The design is tailorable. It can be used for interior and or exterior applications. The architecture is flexible and it's expandable, and it supports one or many sensory panels. The algorithms that we use provide situational awareness, self-configuration, damage detection, and localization of damage. And it supports wireless communication using Bluetooth technology. The sensory panels themselves are modular and interchangeable. We use the same hardware and software, and they are low power consumption, less than 500 milliwatts per panel. The MDDS app that was developed provides a simple user interface, and it's an attractive method to interact with the system. And the embedded thin flexible circuitry that we used with the composites did not appear to impact the composites' overall structural integrity based on some imaging and CT scans that we did of the fabricated composite samples. Next slide. There's a lot of people to thank. This is a list of our folks that are involved. This could not be done without a full team effort. And I think with that, we are finished and we're ready for some questions. Thank you for your time.